So let's go back to hydrogen. We're going to talk about hydrogen, a couple different aspects of hydrogen today. We'll go back to think about the wave functions again, but what we really haven't talked about is the energy. What's the energy level structure of hydrogen? How are the allowed energy levels of the electron? All right, so we're going to talk about that today. And it'll lead us into a conversation which I hope to have on Monday. We'll talk about it a little bit today. Where we're going to find that our typical description of the orbitals as energy levels, right? We say an electron in the hydrogen atom is in the 1s orbital, right, in the ground state. We're going to find that that idea of a 1s orbital or a 2p orbital or that, those aren't very, I want to say that they're not precise descriptions of what the actual energy level of that electron is. All right, so once again, every time I introduce something new, I'm going to tell you that Gen Chem teaches you wrong. And we're going to see that again, that the Gen Chem approximation of an orbital, 1s, 2s, 2p, they're perfectly reasonable approximations. But we'll see that when you peer deeply enough into the hydrogen atom, that approximation, that idea of an orbital kind of breaks down a little bit, okay? It's a little more subtle than that. And the reason why it's subtle is because the orbitals, as we'll see today, are built up, right? Every hydrogen wave function, as we kind of talked last class, can be labeled by 3 quantum numbers. Right, we have the big one, n, right? That's the 1 in 1s. Right? It can be any number from 1 and up. This is what we call the principal quantum number. Right? And this comes from the radial part of the function. Right? The idea that each of these n's correspond in some ways, and in fact, this is the way that Niels Bohr came up with the idea that each of these n's correspond to a orbit of the electron of different radius. So as n increases, the orbit gets further and further away, gets, you know, the radius, the orbital radius of the electron around the proton gets longer and longer, gets further away. Right? So n equals 1 is like Mercury, n equals 2 is like Venus, n equals 3 is like Earth. Okay? So that's actually how Bohr came up with this idea for the hydrogen atom. It's wrong. It's interesting why it's wrong. We won't really talk about that so much, but it gives you kind of an idea of what these n's mean. Right? They're different orbits. Right? And we'll see that in a little bit. That n is if you think about the average position of the electron to the proton, the distance, it gets bigger as a function of n. Okay, so as n increases, the electron gets further and further away. All right, and then we also have the orbital angular momentum number. Let me just write this. This is the radial quantum number. That tells you something about the radius. We have the orbital angular momentum, right, which is the total angular momentum of the electron orbiting. I wanted to distinguish this from total angular momentum because there's also spin that we're going to add. So we're just talking about the angular momentum of the electron orbiting the proton. And I made a mistake last time. I said that L can be any number from 0 to n. It's actually n minus 1. The reason why it has to be n minus 1 is that if n is equal to 1, the only orbital that's allowed in n equals 1 is s, right? There's no 1p orbital, right? And a p orbital is L equals 1. So if n is 1, then the highest value that's allowed for L is 0, which must mean it's n minus 1. Okay, so this will give you that the biggest orbital you can have in the 2s is 2p, right? And then 3 you get d's, 4 you get f's, 5 you get g's, and so on and so forth. Okay, so it goes to n minus 1, right? And this is interesting because when we ignored the radial problem, we fixed the radius of the electron to the proton. Let me record. Oh, I already am. Wow. L can be any number, right? We can spin the electron as freely as possible. But what's happening now is that when we fix n, we have this stable orbit, classically, of the electron around the proton, and that limits how fast you can spin it. Because the faster you spin the electron at fixed distance, you're applying that centrifugal force to, say, the string that's holding the proton and the electron, and you force that electron to stretch, to move away. Right? As you spin something, you get that centrifugal force. And so in order to have a stable orbit at some radius, n equals 1, n equals 2, there's a maximum amount of angular momentum you can put into the system before the system effectively stretches too far and slips the orbit. Right? You don't want to have so much angular momentum that the right? If you have so much angular momentum for, say, let me put it this way. If the electron were a spaceship orbiting the Earth at some distance, if you get that thing spinning fast enough, it'll escape, it'll have enough escape velocity to escape the orbit, right? You won't continue stably orbiting, it'll escape. Right? So the orbital angular momentum is ultimately set by the radius of the orbit. And so it can't be any value. Otherwise, we would have 1d orbitals and 1f orbitals and things like that, which we don't. And so this is, again, the quantum number associated with L squared. Okay? And then we also have the azimuthal number, right, which is our L sub z, right? It's the direction of the orbit with respect to the z-axis of the atom. Right, so this is the LZ quantum number. And the rules are exactly the same as before. You can have any value for m sub L between minus L and L. Right, so let's just double check that makes sense. If L is equal to 1, we're in the p orbitals. If there are 3 p orbitals, which means there's m sub L equals minus 1, 0, and plus 1, as we expect. All right, so that's what sets this. So this, in some ways, I'm just going to kind of reiterate this. This is like the 1s, 2s, it's this number. L squared tells you whether it's 2s or 2p. And m sub L tells you whether you're in the 2px, the 2py, or the 2pz orbital. Right? It specifies which substate you're in. Okay, and with these 3 numbers, we can define any energy level of the electron in the hydrogen atom. Right? This gives us all the orbitals we know. But there's one additional number we haven't considered yet. Right? So this gives you, let me just stop for a second. Right? These 3 numbers give you the classical, I don't want to use that word, the typical hydrogen orbitals. Right? With these 3 numbers, I can specify any of the classic atomic orbitals for hydrogen. But there's one additional number that we don't consider when you do that, which is m sub s, the spin of the electron. Right? So this is actually the quantum number for the projection of the angular momentum on the z-axis, s sub z, quantum number. Right? And this specifies whether the electron is spin up or spin down. Right? The way that we always, right, or the way you fill electrons in CHEM, so you got your 1s, 2s, 2p, and you fill it with an electron up and then an electron down eventually. Right? That's what m sub s are. It's the 2 electron spins. Right? And this just specifies whether in your 1s state you have either spin up or spin down. Okay? And that's how you learn it in CHEM, right? That you have these orbitals, 1s, 2s, 2p, right? And they're just typical orbitals. And you either fill them with an electron that's pointing up or pointing down. Okay? And that's all m sub s does, right? It just specifies the orientation of the spin. But it turns out that there's a subtlety that CHEM ignores, and for good reason. It's not that important in hydrogen. Well, it is important. I'm going to say it is important in hydrogen. And it's very important in larger atoms. In fact, it gets more important as the atom gets heavier. This m sub s, right, this implies that the electron has some angular momentum of itself, intrinsic angular momentum. And so when you put an electron with some intrinsic angular momentum, some spin, into an orbital that also has some intrinsic angular momentum to it, those angular momentum can add or subtract from each other. You can add the 2 vectors or subtract the difference of the 2 vectors. And so you end up getting interactions between the orbit and the spin of the electron. We'll look at this very carefully on Monday. So what happens is that the concept of an orbital breaks down slightly because the angular momentum that comes from the orbital, L, is coupled to m sub s, and depending on the relative contribution of the spin, which is how many electrons you have, and the orbital, you can have different effects. The spin of the electrons in your atom coupled to the angular momentum of the electrons. And this causes the energy levels to split. And in fact, so an orbital, if you say 1s, my electron's in a 1s orbital, it's actually ambiguous. Because you don't know if you're in a state where the electron spin is coupled in a kind of constructive way with its orbital angular momentum, or in a destructive way. And we'll see that they generate different states. And so each orbital, each 1s orbital, effectively one electron in it, is actually two orbitals. There's one state that has, where the spin is constructive with the angular minimum of the orbit, and one where it's destructive against it. And so this concept of 1s, 2s, these typical orbitals, is just an approximation. And what we'll see is that you get to bigger and bigger atoms. Right? You get to the heavy metals, for instance, right? You get to uranium, or even that, iodine for that matter, the high heavy halogens and things like that. This coupling of the spin of all those electrons to their angular minimum really dramatically changes the structure of the atom. Okay? And the idea of an s orbital or a p orbital is kind of nebulous. It kind of breaks down a little bit. But we'll come up with a set of rules that are more precise, that allow us to characterize exactly what state the electron is in, that will avoid all of these complications. Right? That'll be ultimately our goal when we talk about atoms. Is how do we distinguish between atoms, and how do we characterize them precisely, their structure? Okay, so I want to just talk very briefly. I'm going to go back to the orbitals one more time, and I just want to look at them a little more carefully. So again, you've drawn these orbitals before a million times in chemistry. And we always draw these little pictures of the orbitals, 1s, 2s, and the px's, and the p's, and the two p's. You've drawn all of these before. But what are these pictures of? Right? We saw last class when we started to look at the wave functions of the orbitals that these pictures aren't really a good representation of their actual form. Because these are just pictures, and at best 3 dimensions, right? I could add a little bit of, right? These are 2-dimensional projections, but I can draw them so they're 3-dimensional. But wave functions for the hydrogen atom take 3 parameters in and have an output, which is the value of the wave function at a point. They're 4-dimensional objects. So to actually see a wave function, you need to have 4 dimensions. It's a 3-dimensional, a surface that's has 3 parameters, and then the output is the 4th dimension. Okay, so you can't really draw a wave function on a piece of paper. And so we have to kind of cut our losses if we want to visualize things. And this is where we get that, these pictures. This is where we cut our losses. I want to explain a little bit, I think, about where these pictures come from. All right? How do we draw these things? Because what we saw last class is that the wave function for the hydrogen atom, or the wave functions, which are again psi, and they take 3 numbers, n, l, and m sub l. Well, I'm not going to write down the whole formula again because it turns out it's not that necessary for us, but they're proportional to r to the l, that's the angular minimum quantum number, e to the minus r over n, where n is that number, and there's a polynomial l, which is a function of n and l, which takes in a value r over n, effectively. And this right here is just a polynomial. This is, let me think about this. This looks like r to the n plus 1 plus r to the n plus dot 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 as we go down. It's just a polynomial, right? It's just a function of r. And so the important thing to note here is that the wave function again has this exponentially decreasing part here, right? The wave function at any point around the proton, if you fix the angle and you walk down the radial line, right? You just take that electron at the same angle and just keep walking out, the wave function extends forever. Okay, but these pictures don't extend forever. They're just spheres and lobes and things like that, right? They're not real wave functions. They don't exist to infinity. Right, this function, right, so in general, this function goes to 0 as r goes to infinity. Okay, what that means is that in a 1s orbital, again, 1s is spherical, so it doesn't matter which angle you're at, but there's effectively non-zero probability of the electron being anywhere with respect to the proton. It could be on the moon, for all we care. Okay, so these pictures are somewhat inaccurate because they express something finite about something that's infinitely defined. All right, and I want to talk just very briefly to show you where these pictures come from. Why do we have to kind of cut our losses, and how do we do it? Okay, well, remember that we don't actually observe the wave function. We observe the square of the wave function, right? Remember, the square of a wave function tells us the probability of where to find that particle. So what we actually need to measure first not psi, but remember, we want to calculate psi squared. Okay. All right, so now we have to think about, okay, this is actually what we're measuring, right? And I want to think about the probability of finding my electron as a function of radial distance, okay? Right? I'm not going to worry about angles so much right now because the spherical harmonics tell us something about the angle, right? In the 1s orbital, there's no angular dependence. So I'm curious about the actual probability of finding, say, for instance, in the 1s orbital, where the electron is on average. Okay, so let's do that. Right, so let's ask the question, what's the most probable, or what's the mean value of the proton electron distance in the 1s state? Okay, maybe this will teach us a little bit about, maybe if we can calculate this, maybe we can think of a picture. What if we fix instead we consider drawing our wave function, fixing the distance, r, to the most probable value of it, right, at the peak of your psi squared. Right, so if we can calculate what the most likely position of the electron is, let's fix it there and then plot the wave function as a function of angles. If we do that, then if we fix r, then our plot is only two parameters, theta and phi, and therefore the output is the third dimension. We have a three-dimensional surface. We can plot that. So let's do that. So let's first calculate. Let's just do the same thing we've always done, which is we're going to calculate the average position of r for the 1s state, right? R sub 1s. Okay, so what we need to do is plug in, right? We're going to take an integral over something, not sure yet. Take an integral over all space. We'll have to define what that is in a second. Of our wave function for the 1s state. That's going to be the 1, 0, 0 state. Right, I'll just remind you this is n, l, and m star. Right? And then times the r operator times psi 1, 0, 0. All right? And we got to integrate this over a volume, right? Because it's three-dimensional. So we have some volume V. Okay, but we know what that volume is. We did it. It's a sphere. Right? We're going to integrate this over a sphere. So let's do that. Right? We can choose to do x, y, z if we want, but let's just keep it simple. We've done everything in spherical coordinates. So we've written down a long time ago when we talked about spherical coordinates what this integral looks like. We have an integral from minus infinity, oh sorry, let me start over. I apologize, not minus infinity. 0 to infinity. That's going to be for the r. I'll just put it here. That's our r integral. We have an integral from 0 to pi. This is going to be our theta integral. And we have our 0 to 2 pi integral, which is our phi. This is theta. Let me clean that up a little bit. Theta, and this is phi. All right, so we have a triple integral over our 3 coordinates. And if we go back, what does dx, dy, dz convert to in spherical coordinates, right? We have because of the chain rule, we need to adjust our integration bounds a little bit. Right? And so what we get is r squared sine theta. This comes from the fact that we're going from x, y, z into r theta phi. This is what we call the volume element. And then now we can add our integrals into here, right? So we have psi 1, 0, 0 times r times psi 1, 0, 0. And then we need to write our little integral, our little differential elements. So the first integral is theta, so we're going to have d theta. Our next one is d phi. The next one is d theta, and then dr. Okay, so this r squared sine theta is always there in these integrals, right? This is always something that we have to integrate when we integrate in 3-dimensional coordinates, because when we go from a volume element in x, y, z to a volume element in spherical coordinates, we always gain this r squared sine theta term. Okay, so that's always there. So let's go ahead and plug some things in. So this integral, we can separate a few things. So first this is always a really great task when you're doing multiple integrals, is to separate each of your terms into a product of 3 separate integrals. So what we're going to do is we're going to take this triple integral and convert it into a product of 3 single integrals, right, which we're allowed to do, at least in this case. Because everything's linear, we're allowed to split things. So what we're going to have is something that looks like, let's go 0 to, let's do the d theta first. D theta, sine theta. All right, so we have an integral of sine theta to do. We have an integral from 0 to 2 pi of d phi. Right, there's no phi dependence in the 1s orbital, so there's nothing to integrate for phi. It's just an integral of the volume element. And then we have our kind of complicated r integral, which has a factor of r squared from our volume element. And now I'm going to go ahead and plug in the wave functions here. So the 1s wave function I wrote down for you guys last class, but I'm just going to go ahead and plug it in for you here. So it is 1 over pi, square root of pi, sorry, times 1 over a naught to the 3 halves, e to the minus r over a naught. That's our wave function for the hydrogen, for the 1s orbital, right? It's just e to the minus r, super easy. We also have a function, we have our little operator r, and we have one more wave function, right? We have to take the square of the wave function. Now, I want to stop here for a second. All right, we'll evaluate this integral. All right, no problem. It's not too hard, actually. It's a lot of work. It looks like a lot of work, but we'll simplify it out. It's pretty easy. The thing that I want to point out is that if I ignore this r, right, this is our operator, which we're calculating an average for, right, the average distance. If I ignore this, right, if I just set this to 1, get rid of it, we're taking an integral of psi squared And every time we take an integral of psi squared along r, there's always this r squared. Right? So, in fact, in spherical coordinates, so remember in xyz coordinates, in like the angular momentum, sorry, not angular momentum, the harmonic oscillator, or in the particle in the box, our probability was psi squared. Right? It's the thing that you integrate, the thing that goes within the integral, the thing that you integrate and you get 1 out when you integrate over the whole thing. Right? The psi squared should integrate to 1. In order for this to happen in spherical coordinates, the thing that you actually integrate over all space to get a probability of 1, right, the normalized wave function squared, is you need to also have r squared here. R squared is an additional factor that we have to include because of the fact that this is a three-dimensional object and we have to average over a sphere in order to calculate precisely what the probability of r is. We have to account for all the different angles and all the different behaviors around the sphere, and this gives us this additional factor of r squared. So I just want to write this really quickly, is that in Cartesian coordinates, x, y, z, that psi of x, y, z squared is our probability. But in spherical coordinates, the equivalent is r squared times psi of r theta phi squared. Right, there's a factor of r squared that is included. Right? We always have to have this additional r squared in our approximation for our probability. And this is just for the fact that, again, we're not doing things in a linear space. We're doing things in a spherical space. And we end up getting this extra r squared term from it. And again, this just comes from the chain rule in our transformation of our coordinates. Okay? So I can't, when I write psi squared and for the hydrogen atom, I'll get the wrong answer. So I always have to include this r squared. All right, so let me show you the consequence of this, and then we'll go back and solve the integral, okay? So we'll just hold off on that integral for just a second. So let me show you the consequence of this. So this is important because if I instead said that the probability, if I said that the probability of electron position in a 1s orbital is just psi squared, then what would psi squared be? Well, psi squared is, I'm just going to quickly write it down. It's proportional to, I'm just going to ignore all the constants. Maybe I'll write them down, actually. Just a sec, sorry. Psi squared is 1 over pi AO cubed, 1 over pi AO cubed, e to the minus 2r over a naught. Okay, so that's psi squared. If I just take a normal square of it, right, what does this function look like? Right, what if I plot this as a function of r? Well, the maximum value of this function is at r equals 0. Right? R equals 0 gives me e to the minus 0, which is 1. Right? So the value is at 1. The maximum value is at 1 over pi AO cubed. So the psi squared implies that the most probable location for the electron is at r equals 0, and it decays like this. Right? Well, that should be a problem, right? That should trigger a concern in your head, because what this is saying is that the most probable location for the electron in the hydrogen atom is right on top of the proton. Okay, so that can't be right. Right? This implies that they're constantly touching each other, right? And I just said that the electron has to be some distance from the proton. And so if I were just to take psi squared, you wouldn't get the right answer, right? You get this argument that it's at that the most likely probability is that it's at r equals 0, which is obviously not true. Okay, so but now what if I instead do r squared sine psi theta, or psi squared, sorry. Right, what if I instead plot the proper thing, which is r squared psi squared. Right, so the only difference now is now psi squared looks like 1 over pi AO to the third r squared e to the minus 2r over a naught. Well, now if I put r equals 0 in there, the wave function psi squared is 0. Right, so now there's no probability for the electron to be on top of the proton. So if you plot this function, you end up getting something that looks much more rational, maybe is the right word for it. Sorry, I'm just looking for my results here. There it is, right? And if you plot this function now, r over times multiplied by r squared, psi squared, that's your y-axis, then the function is 0 at r equals 0, and it increases as r squared until the exponential starts to get increasingly small and it turns down and decays away. Right, so by including this r squared factor, which again comes from the fact that we're averaging over a circle, we get something that's much more physical, right? That the probability of this 1s electron is somewhere away from the proton, as it should be, right? So this means that there's some finite distance that the electron is at, and this is the average value of r for the 1s orbital. Okay, this is why I wanted to calculate that average, because this will tell me exactly where the electron is typically for the hydrogen atom in the 1s state. Okay, so let's go back to that integral again, and let's calculate this. So I'm just going to kind of stick it at the bottom. We're almost done. So r is the integral from 0 to pi of sine theta d theta, the integral from 0 to 2 pi of d phi, times the integral from 0 to infinity of, it turns out once I do all the math out, sorry, let me just multiply it. Let me fix a couple things here. It ends up being 4, sorry, no it doesn't. All right, let me just remind myself. I'm canceling out some pi's accidentally. I need to keep the pi's in. Just a second. Okay, yeah. This ends up being 1 over pi AO cubed times r to the 3, r cubed, e to the minus r over a naught dr. All right, and the r cubed comes from the fact that we have that r squared that we just talked about, and there's also the r from the operator, the distance operator. So you have a net r squared, r cubed. Okay, so we have some integral. This is very easy to do. You can do this by parts, or Wolfram alpha will go just fine, but this is just a by parts integral. Let's work out the angular part really quickly, because you're going to see this integral every time you do an integral in 3 dimensions in spherical coordinates. You will always get this. Right? You get the sine squared d theta. That's the volume element portion. And that's when you go from dx dy dz to dr d theta d phi. You always get the sine theta. We don't have any dependence on theta and phi in our wave function, right? The 1s orbital is spherically symmetric. So this is just integrating over the spherical part of the volume, right? We're just integrating the angular part of the sphere. And so this number just ends up being fixed. Right? It's just kind of common. So let's do the easy one first. Well, I guess we'll just do it in order. So the first integral is the integral, let's do this one, the integral of sine theta d theta. What's the integral of sine theta? It's just cosine. Wait, negative cosine. Negative cosine. Negative cosine, that's right. The derivative of sine is cosine. Yeah, I apologize. And so let's do negative cosine of pi is what?
0.
No. It's the x value for pi. Sine of, so the integral, sorry, maybe I'm confused, sorry. The negative cosine of phi, let's evaluate the integral. So sine of theta d theta is minus cosine. So let's do it at the bounds. What's minus cosine of pi? That's cosine of pi.
So
1. Let's grab a marker really quickly. Let's just convince ourselves that we're right here. We've got a circle. What's the coordinate here? 1, 0. The coordinate here is 0, 1. Sorry, minus 1, 0. All right, we're doing pi. So cosine of pi gives you the x value for this point. That's minus 1. So minus cosine of pi is 1. And what's the cosine? And then we got to subtract off the lower bound. So what's the cosine of 0? This is the x coordinate. Well, no. 1. It's the x value, right? So that means it's minus 1 because it's minus cosine. So we have 1 minus minus 1. It's 2. Okay, so the integral from 0 to pi of sine theta is just 2. Really, really easy. So we have a 2 here. And then let's do the next integral, d theta. Right, that just gives me theta. So we evaluate so we have 2 pi minus 0. So it's just 2 pi. Okay. So in general, the theta, the volume, the integral of a sphere around its angular coordinates is 4 pi. All right. 4 pi. All right, so it's 4 pi. And then we have this complicated integral of r, which I'm going to do a little bit of u substitution. This ends up being 0 to pi of 1 over pi a naught cubed x cubed e to the minus 2x. Sorry, I forgot a factor of 2 in here. It's 2r e to the minus 2x dx. Okay, and again, I could do this integral in Wolfram alpha. Really, really easy integral to do. It's just a particle. It's just by parts. You do parts by parts 3 times, and the answer you get is beautiful. Very simple. It's 3/2 a naught. So the average value of the electron in the 1s state, the mean value, is 3/2 a naught. Right? This is where a naught comes from. Right? A naught is parameterized as effectively, basically, let's say off by just a small amount, but the average position of the electron in the hydrogen atom. And so A naught, remember, is about 0.53 angstroms. So on average, the 1s electron is about 1.5 angstroms away from the electron, from the proton. And so I'll just say this is roughly 1.5 angstroms. That's how far it is. Okay, so this is all starting to come together. This is where the A naught, that's why the A naught number is so useful, is that everything about positionality in the hydrogen atom or any atom is a function of A naught. A naught is our length scale, and everything is kind of on, the fundamental length scale of chemistry, if you will, which is the length between the proton and the electron, is about A naught. Right? It's a fundamental constant of chemistry. Okay, so the idea here is, again, you can do this analysis for any of the orbitals. Again, the integrals get kind of nasty as you get to bigger and bigger integrals, because as you get to the p orbitals, for instance, you're going to have some dependence on theta and phi, some sines and cosines you're going to have to integrate. But in general, it's not too bad. I'm not going to have you guys do these integrals really, but I think it's important to look at them. And so when you look at the different, excuse me, sorry, when you start looking at the different orbitals this way, we can look at, say, 1s. I wrote this down that if we plot 1s, and what we're going to plot, all right, let me erase this just a bit. I need a little more space. What I want to plot, r versus r squared, psi squared, divide it, and then we get rid of the length scale, which is AO squared. This is unitless probability. Because again, the probability here of position, right, the probability is r squared psi theta, so the probability has units of r squared. So we're just going to divide it by a naught squared to make it unitless. Right, so this is unitless probability, so we can plot all of them on the same scale. And I'm going to plot it versus r over a naught, sorry. And so the 1s orbital, so for 1s, we have this really, really nice sharp kind of graph that looks like this. Right? And this is at 1.5. R over a naught is at 1.5. Right. And this is our 1s orbital. Again, it kind of looks like the n equals 1 state for the harmonic oscillator, the n equals 0, the ground state, right? It just kind of looks like a broad distribution. There's no wave-like pop properties. It's just got one wave, right? It's just got no nodes. There's the only place where it has 0 probability of existing is at r equals 0. The only node is on the proton. Right? And so let's look again at the 2s. Let's go up a level. Let's go to look at the 2s, do the same thing. And what you see in the 2s is, as I showed you last class, is the node-like structure. Right? There's a and this is at about 1.5. So in the 2s orbital, there's kind of, as I said, there's kind of two shells of probability the electron can be in. There's kind of the closed shell right here, and this is a region where the 1s electron doesn't really have a lot of probability to be. And in fact, at the position where the electron typically is in the 1s orbital, it can't be in the 2s orbital. There's a node there. And in fact, the electron tends to want to be closer and further away, right? The largest peak is further away. And I can give you the exact number for this in just a second. So this is 0, 1/2, almost 3 halves. 3 halves n squared. So this is 4 times 3 halves. That's 12 halves. That's 6. So this peak right here is at 6 a naught. Right? So the electron is continuously getting further and further away as n goes up, or as n goes up. Right? It keeps pushing itself further and further away. We can look at the 3s orbital as well. And again, it starts to have that wave-like structure we expect, right? We expect these things to have ebbs and flows, right? Because these things are still electrons. Right? So the 3s orbital, this is the 3s. Like this. Right, and this average, this peak right here, which is the largest probability of where it is think about this for just a second. This is n squared is 9. 9 times 3 halves is 20, so it's 12 AO. Right, so as the electron gets more and more excited, right, the orbit's getting further and further away, it's spinning faster and faster, there's more and more kinetic energy, less potential energy, and it's further away from the electron, or from the proton. Right, so that natural structure that we think about the electrons being further apart as the orbital energy increases is 100% true. But again, there's still wavelength, right? There's still probability that the electron can be closer, like can be quite close to the nuclei even in the free s orbital, but the probability of that happening gets smaller and smaller as energy increases. Right? And let's just look roughly at the other orbitals. So the 2s orbital, or sorry, the 2p orbital, again, you don't really see along the r around the radial direction, you don't really see that lobe-like structure in the 2p orbital. It kind of looks like a hump as well. And in the 3p, again, we start to see the node-like structure appear. Okay, you can kind of think that, and it's not that surprising, if I go to the 3d orbital, which is really quite interesting, it also doesn't have any nodes either. Or this is the main 3D orbital. It's just kind of broad, like this as well. Right, so again, this is the lowest lying p orbital, right? This is the lowest lying orbital of L equals 1. This is the lowest lying orbital of L equals 2. That's the lowest lying orbital of L equals 0. Right? These, in terms of the angular momentum, they're fundamental waves. So they don't have any nodes. So the nodal pattern comes from this combination of having nodes that arise from having excitations in the orbit, the n increasing, but they also can come from the fact that L also increases as well. So the 3D looks like this, and the 4F, right, also looks like this as well. Right? It doesn't have any node-like characteristics to it. Okay, and in fact, there's some really, really nice formulas here. I'm just going to write them down. They're not super important, but I think they're interesting to look at. Is that you can generalize the position of the electron as a function of the coordinates, or of the numbers. So if I want to calculate R for n, L, and m sub L, there's a really, really nice formula for it. It's a naught n squared over z. I'm just going to write z is the charge of the nucleus. So for hydrogen, it's 1 times 1 plus 1/2 times 1 minus L times L plus 1 over n squared. Okay. So again, this makes a lot of sense. Right? As n increases, the average position of R also increases. Right? The electron's getting further and further away. But as you start to spin the electron faster and faster, interestingly, that actually brings the electron, it pulls the electron in a little more closely, right? The radius as L increases here. Let's just look at it really quickly. Let's just do the quick calculation here. Right, so let's look at, for instance, well, we know what R for 1, 0, 0 is. That's the 3s, or that's the 1s orbital. R for 1s. That's going to be a naught times 1 squared over 1. 1 plus 1/2 times 1 minus 0 over 1 squared. Right? And that is 3/2 a naught. Right? Easy enough calculation. And then let's try the 2s, right? I wrote that down earlier, but again, it's not too hard to do. This is going to be 4a naught times 1 plus 1/2 times 0. So that's 4 times 3/2. So that's 6a naught. And then let's look for R2p. Well, again, we still have that 4a naught on the outside. But now we have this 1 plus 1/2. 1 minus, and now L is 1. So we have 1 times 2, that's 2 over n squared. N here is 2, so that's 2 over 4. I'm running out of space here. So that's 4a naught times 1 plus 1/2 of 1 minus 1/2, so that's plus 1/4. And that's going to be, what is that, 4 times 5, that's 20/4. That's 5a naught. Right, so interestingly, in the 2s orbital, the electron was on average at 6a naught. And as I start to spin it up, it actually pulls the electron in a little more closely. Well, it seems counterintuitive because I explained that as you start to spin it faster, it should push it out further. But there's a fine balance here between the charge attraction and the angular momentum. And it turns out that when you pull this electron, you rotate this electron like this, it actually pulls it in a little bit at fixed n. So at fixed n, right? So there's this very, very fine balance between the orbital radius, which is n, and the angular momentum, which is L, at fixed orbital radius, at fixed orbit. The faster you spin that electron, the closer it pulls in. And then as n increases, it gets further and further out. But if you fix n and increase L, the electron actually pulls in. The system actually, instead of it having a centrifugal force out, like you would expect classically, the system actually pulls the electron in on average. Actually makes it more compact. Now this is partially one of the reasons, not the only reason, why double bonds, carbon-carbon double bonds, are shorter than carbon-carbon single bonds. But one of the reasons why they are is because the double bonds, again, are due to the fact that you have electrons and p orbitals interacting. They tend to be closer to the nuclei, and so the bond lengths between two atoms with electrons that are closer to nuclei also are closer. Right? Everything's more compact. So one of the reasons why this is partially the reason why double bonds, triple bonds, they tend to be stronger on average per bond than a single bond because of the electrons being closer, more closely bound to the proton. Right, so this is very counterintuitive. Right, this was not expected, but it's a fact of the matter, and you can see the little seeds of this throughout chemistry. That electrons in highly excited angular momentum states, up to a certain point, they tend to be very, very close, kind of closely bound. Bring them in. Which I find very interesting. It's very uncharacteristic of things that orbit. Now, one of the interesting things, again, I just want to give you a little bit of historical context, is that when Bohr first came up with this idea, Bohr said that the idea is that the electrons have these stable orbits, just like the planets have around the sun. And you have different orbits, quantized orbits that are allowed, right? These are the ends. But the problem with that argument is that in a classical orbit, okay, so let's imagine you have the Earth and the Sun. The Earth has to have angular momentum in order to orbit, right? If the Earth was just stationary, it had no angular momentum, was not orbiting, right, what would happen? Eventually it would get pulled in, right, by gravitational attraction. Right? So in order for an orbit to be stable classically, the orbit must have angular momentum. You've got to have it spinning, otherwise gravity is going to pull it in. But here I've shown you a stable orbit of our electron that has no angular momentum, the 1s state. 1s state, the electron formally has no orbital angular momentum. It's not orbiting in the sense that you can think of it as, but it's perfectly stable. Right? Bohr didn't realize this until much later. Bohr's model of the hydrogen atom, which is the one that you probably see those pictures of with the little nucleus and the circles around it, and the classic picture of the atom, that picture's wrong because it implies that the atom must have angular momentum. That would imply that the lowest energy state of the atom would be the 2p orbital, the 2p state. That's the lowest state with the angular momentum of 1. And so this idea of orbits doesn't really work, right? And this is another indication of why it doesn't work, because in orbital theory, in orbits of planets and stuff, centripetal forces pull that system, stretch that system apart as the faster you spin it. But in electrons, in an atom, the faster you spin it, the closer it pulls it in. Right? Very interesting. Completely opposite. Despite the fact that we literally started this theory thinking about classical orbits, right? Thought about just a particle moving around another particle. The result is opposite. Okay, so that's kind of all I have to say about these orbitals. Again, I'm going to talk on Monday a little bit more about the intricacies of not the shape of these orbits. I didn't really get to the point of the shape of the orbits. I'm sorry. So here's the important thing. So these pictures that you see, everything that I've been discussing here, these pictures that you draw of these orbitals, what they do is they fix the radius to the most likely position. Right? So when you draw a 3s orbital, you're going to draw one of the shells here, one of the shells here, and one of the shells here. Okay, and in a 1s orbital, you draw a sphere with radius 1.5 or radii. Right? And the p orbitals, right? We fix the distance between the electron and the proton at this distance right here, 6a naught or 5a naught or whatever it is, 5a naught. Now our wave function is just a function, or probability is just a function of the angle, and that's when you get to see those beautiful lobes. Right? So if I fix this here, fix r to 5a naught, and then plot this on a function, plot this on a graph of z and x. Right? Then what we get, we plot the angular part, right? But this is the amplitude of the wave function where the wave function has value fixed to this radius here. Okay, so all the electrons that are being shown by this orbital are all fixed to this distance. Right? That's where these pictures come from. We reduce the dimensionality of our wave function by fixing the radius to something reasonable. Pick the most probable place. And then plot the angular part of the function. Okay, so these pictures are only half the story. You only get to see them from the angular point of view, but deep inside of it, there's a radial wave function that's defined from 0 to infinity, and as you can see, they're very complicated, and they're not all that obvious. Okay, and so you have this rich structure that you can't really see when you draw these pictures, because you lose that dimensionality along the radii. Okay, that's all I wanted to say about that. It was just I've talked about everything, but I didn't conclude it. Okay, so what I want to do for the last 15 minutes is to talk about the elephant in the room. We've been talking about orbitals. But remember, we haven't talked anything about energy. What are the damn energies of these orbitals? What are the allowed energies of the electron? And maybe even more interestingly, right, we have these orbitals that are a function, right? We get a different orbital depending on the angular minimum and n. Right? We have dependency on 3 quantum numbers. Is the energy also dependent on all 3 quantum numbers? And the answer is no. So one of the most amazing things about the hydrogen atom is that the angular momentum, in terms of energy, the angular momentum is completely averaged out. There is no dependence on L. And the only thing that determines the energy of the electron in the hydrogen atom is N. Right? And so when you solve the Schrodinger equation for the hydrogen atom, well, this is hydrogenic energies. The allowed energies of the hydrogen atom. All right, I'm going to write this a couple of different ways. But you get this really amazing equation. I think it's kind of cool. That's just a product of all of the constants. 32 pi squared, epsilon naught squared, h bar squared, times 1 over n squared. All right, so you get this big, so the energy for this system, you get this big prefactor. It's got the mass of the electron times the charge of the electron to the 4th divided by 32 pi squared, epsilon naught squared, h bar squared, just numbers. And the thing that's important is just the 1 over n squared. Right? This function is only dependent on the value of n. So another way to write this, it turns out, I'm going to write it a couple different ways. E squared over 8 pi squared epsilon naught a naught times 1 over n squared. Okay, so that's another way to write it, right? So as you can see, it's very interesting. If a naught is some function of these constants. So what is a naught? Well, we can just do a little bit of algebra. Right, what you find from this, just as a side note, I think it's quite interesting. On a side note, a naught, which is the Bohr radius, is 4 pi epsilon naught h bar squared times the mass of the electron times the speed of light squared. And this is about 0.53 angstroms. Okay? So very, very interesting. You get a length from just combining some fundamental constants of the universe, right? This is pi, which is perhaps the most fundamental constant of them all. The question of whether pi is unique to this universe or not is a different question. But sure, pi is fundamental. Epsilon naught, that tells you how conductive the vacuum is, right? That's fixed for all universe. Of course, each bar is a fundamental constant. The mass of the electron and the speed of light. Right? So all of chemistry's length, right, the length scale of chemistry is entirely set by the physical parameters of the universe. Right? The chemistry we see is entirely defined by these 4 numbers, or 5 if you include pi as a fundamental constant. Whether it is or not is whether, I'm not sure. Okay, I think that's really cool, you know, that they, you know, this defines the bond length effectively, right? If A naught was different, the bonds chemistry would look a lot different. And A naught is only dependent on fundamental constants, right? The universe fixes this value for us. And perhaps if we're just lucky that we live in a universe that gives us a number that gives us chemistry. Because if A naught were tens of angstroms or something like that, we might not have the same type of chemistry that we have today. It's an interesting thing to think about. But the important part about this is that the only thing that the energy is dependent on is n squared. N squared. There's no L here, there's no M sub L. It doesn't matter if you're in the 2s, the 2p, or the 2d. Well, there's no 2d. The 2s or the 2p, or the 3s and the 3p and the 3d, they all have the same energies. Or at least they do at this level. All right, so there's another way to write this. One more way to write this, and I think this is probably, I have a couple, actually I have 2 more ways to write this. One is, this is the way that classically it's written for a long time ago. Hc times this constant R infinity over n squared. Right? And R infinity is called the Rydberg constant. And it has an exact value of 109,773.731 wave numbers. All right, so this number will tell us something about the energies in wave numbers. All right, if you go back a long time ago in this class, and I talked a little bit at I think it was the first or second lecture. We looked at the spectra of hydrogen. And we said that, hey, there's these discrete lines. And this guy named Balmer used some numerology and came up with a formula to predict where the lines show up. And the exact formula he comes up with is this one right here. He comes up with that 110,000 wave number. All right, he gets it completely from just fitting a spectrum to, he just made up a function. Right? He doesn't have any knowledge of the hydrogen atom. And so Rydberg was the one who reanalyzed Balmer's work. It's named after him. But this constant, this formula for the hydrogen energy levels was determined experimentally without any knowledge of any of the physics. no idea how the hydrogen worked, right? I just told you Niels Bohr, who in some ways is one of the inventors of quantum mechanics, he even originally got the model wrong. His advanced model in the early 1900s, this idea of having these stable orbits, that's wrong. And even with that theory, he can still reproduce this value. Right? So the idea is that the angular minimum of the electron ultimately does not matter in terms of energy, as far as we can tell right now. It only depends on n. Okay, so the orbit ultimately determines the energy of the orbit determines the energy of the electron. Okay, so what do you get now? Okay, so let's think about the spectroscopy of this very briefly. Right, we want to do some absorptions and emissions, right? We want to know what are the energies or the frequencies or the wavelengths, whatever you want to think about, of absorptions from some number n to n prime. Right? Maybe we want to take an electron from n equals 1 to n equals 3. Right? What's the energy of that? All right, well, but we have a really nice formula to do that, right? So all we have to do is calculate the energy difference. Right? And that's super easy. It's 1 times hc r times the Rydberg constant times 1 over n squared minus 1 over n prime squared. Super easy. Okay. But the interesting thing is that if you think about it, as n increases, let's think about the spacing between n and n plus 1. Well, the difference between them depends on the difference, the inverse of those numbers squared. So the bigger the number n, the smaller the spacing becomes, right? The difference between 1, let's say 1 over 1, n equals 1 and n equals 2, 1 over 1 minus 1 over 4, 1 to 2, that difference is on the order of 3/4, right? So for n equals 1 and n equals 2, this is going to be 3/4. But for n equals 11 and n equals 12, you have, or n equals 12 and 1/12 minus 1/11, that's much smaller than 3/4, right? So the energy level spacings for the hydrogen orbit, unlike the Schrodinger equation, sorry, oh my God, I'm talking too much. Unlike the harmonic oscillator, where the energy levels are equally spaced, and unlike the particle in the box, where the spacings between the energy levels goes as n squared, they get bigger as you go up. The hydrogen atom energy levels get closer and closer together as you go up. Right? So this means they get scrunched up. So you can start drawing some pictures here. Right? We can just take this idea here and draw some energy levels, right? So the first energy level is n equals 1. Right? And then there's going to be some level n equals 2 at some energy difference, and we can certainly calculate it. But as we continue to go up to n equals 3, n equals 4, the spacings get smaller and smaller. Right, so what is this difference? Well, this difference is going to be the difference between, it's going to be 1/4 times this number. So let's just kind of say it's on the order of 1/4. Right? Of course, they're in the units of HCR. Right? We're in unitless energy here. And then we go to n equals 3. And what's the difference here? Well, it's the difference between 1/9 and 1/4. Which is, geez, I can't do fractions. What's 1/9 minus 1/4? Okay, so this is, I'll just write, this is 0.25 in our reduced energy units. This one is 0.13. Okay, and then n equals 4 is even closer. That's going to be the difference between 1/16 and 1/9. Which is 0.001
0.048. Right? And so as you continue to go up, the energy levels just keep getting closer and closer and closer and closer. And they just keep getting closer and closer together. Right? But there's theoretically should be infinite of them. Right? But they keep getting closer and closer together, so eventually the spacings will go to 0, which means that the energy levels must converge to some value. Right? They must, because they're all getting closer and closer together as 1 over n squared. The difference between them will go to 0 as n goes to infinity, which means they reach some asymptote. Right? There must be some energy that's a maximum energy for the hydrogen atom, right? Which we could call n equals infinity, right? Whatever that is. Right? And the levels just keep getting closer and closer and closer to that limit. Now, of course, what is that number? Well, so what is E infinity? Okay, well, E infinity is going to be the difference between E0 and E infinity. Okay, but E infinity is, remember, it goes as 1 over n squared. This goes to 0. So the energy of infinity, I'm sorry, I have this backwards. Sorry, I apologize. I have this the wrong way. I need to do the upper state minus the lower state. So it's going to be E infinity minus E naught. And E infinity is going to be minus HC, oh, I'm almost done, guys, over infinity squared, which of course isn't real, minus HC R infinity over 0 squared. Right? And of course this right here goes to 0. So this n equals infinity limit is at minus E naught. Well, what is minus E naught? Well, minus E naught is the Rydberg constant, 109773. So this energy is 109773.731 wave numbers. Or, I'm going to give you the other number. I just need to, yeah, which is equal to 13.6 electron volts. This number is how much energy it takes to remove the electron from the hydrogen atom. This is the ionization limit. This is H+. Okay, so this number is the ionization energy of H to H+. Right? That's the enthalpy. That's how much energy you need to put in to remove the electron. Right? So what we have in hydrogen is a series of sequential levels that go up to infinity, and eventually they converge to the point where if you just put enough energy into it, the electron's gone. And as you can see, the electron could be not infinitely far away from the hydrogen atom, but we could populate it at n equals 1,000 or n equals 2,000, right? It could be right below that ionization limit, and you still have a bound electron. There are infinite levels below that ionization limit. Okay, we'll look at that a little more carefully tomorrow. And we'll come back to the structure a little bit more, look at this a little more carefully, look at the spectroscopy, and that will allow us to start thinking. We'll find a little scary moment that we're going to have to reconsider our electron structure, these orbitals, and that will come from this energy level structure. Okay, so we'll see that on Monday, guys. Have a good one. Me